7b97z40, line 22, 7b97z40, Rydberg Photon Excitation Rubidium atoms, quantum gates, dipole moments by Wow Seti. Alien radio signals there. This is excitation of atoms, photons, quantum gates, dipole moments found in the PDF test results on a blog used for core engine on a UFO spaceship found in the wild data line 22. August 21st, 2013, the previous video. Line 22, 7b97z39 is DARPA Rubidium Bose Einstein atom superconducting lattice signals formula by Wow Seti. We're talking about the subwavelength-diameter optical fiber and atom trapping and guiding. The keyword was rubidium atoms, and I got it from the blog www.mpq.mpg.de. Quotes and PDF results were found on a blog. This is from 2004. It's Rydberg excitation in a gas of ultracold rubidium atoms. We successfully demonstrated the controlled Rydberg excitation is a gas of ultracold rubidium atoms. This is one important milestone of the project, quantum gates with neutral atoms and periodic structures. Link Project D. Rydberg, funded by the Lattice Baden-Württemberg. Rydberg atoms in a state with a high principal quantum number, have a large dipole moment, and are therefore of general interest. For example, the dipole blockade of two neighboring atoms can be used to realize a quantum phase gate with neutral atoms 1. Rydberg excitation of rubidium can be done in two ways, either by excitation directly from the rubidium ground state to a Rydberg state, or a two-photon transition via an intermediate state, see figure 1. For single proton excitation, a laser at wavelength of about 300 nm is needed, and hence typically large bandwidth pulse lasers are used. In order to have a small bandwidth laser, we decided to build up a blue CW laser system and to perform a two-photon excitation, see figure 2. In this setup, we used two 960 nm laser diodes in a master-slave setup, and frequency doubled this wavelength in a doubling cavity to 489 nm. Rydberg excitation of RB atoms by neural alignment laser system. So there's the level scheme, 87 RBs, and it shows the diagram. So this is figure 1 is rubidium Rydberg transitions. For the excitation of the atom to a Rydberg state, a two-photon transition is used. Okay. Rydberg excitation experiments start from an RB-MOT. In such an MOT, RB atoms are laser cooled down to a temperature of about 0.1 MK. The MOT cooling laser transition at a laser wavelength of 780 nm can also be used for the two-photon excitation to the Rydberg state. During the MOT phase, the blue laser is pulsed onto the MOT for 0.1 ms at a given electrical field to excite the atoms to the Rydberg state, see figure 2. After the excitation, the electrical field is ramped up and the Rydberg atoms are field ionized. The resulting ions are accelerated toward the microchannel plate and detected. So here's our diagram of figure 2, which was mentioned twice. Experimental setup for the Rydberg excitation. So you have your multi-channel plate, an MOT, reflection of MOT beams, a gold plate, and 480 nm laser. The rubidium MOT is permanently running at a rate of 20 Hz. The blue laser is pulsed onto the MOT to excite the atoms to a Rydberg state. At the same rate, the atoms afterwards are field ionized and detected with the multi-channel plate. Figure 3 shows the typical time-resolved ion signal of the MCP blue curve. Some Rydberg states show an ion signal even without field ionization ramp, green curve. Okay, so you got your green just below the blue. And then the black one is your E field. This is a sketch of the experimental sequence and time-resolved NCP signal after an excitation pulse of 0.1 ms. An electro field ramp is applied, black curve, and the resulting ions are detected by the MCP blue and green curve. By changing the electro field and or the laser frequency, different Rydberg states can be excited. The results of such a measurement is shown in figure 5 together with the corresponding calculated Stark mach of rubidium. To take the data, we stabilized the blue laser to a given frequency and changed the electrical field during the excitation. Each data point in the picture at the right side is an integrated NCP signal like Fig 3. Each line consists of about 1,000 single measurements and takes about 50 s. By changing the laser frequency and scanning again the electrical field, a stark map for the n equals 40 manifold could be measured. In the future, we will investigate the coherent dynamics of the two-photon Rydberg excitation, and we hope to observe the dipole blockade effect in ultracold gas of Rydberg atoms. So here's the RB stark map, and it goes from minus 40 to positive 40. E field BCM, and then we have some figure 5. Left hand side is calculated RB stark, and the right hand side is the measured part of the n equals 40 RB stark map. That's your E field BCM, and those are the references for from 2096, www.pi5.unistuttgart.de. Keyword is rubidium atoms. Will be in the next video. Thank you for watching.